All right, guys, so we're finally to polar coordinates and graphs. Now, what a polar coordinate is, all right, is very close to what a Cartesian coordinate is, but instead of having an x and y coordinate, we have an r and a theta, which means r stands for the length of the radius and theta is the angle, of course. So we'll always start from the positive x-axis. So, for example, this one right here, this example, you have pi over 4. Right, that means that this angle right here would be pi over 4. And then this point is located right here on 2, all right, which is, if you notice, they do it where this is 0, this is 1, this is 2, and that's 3. All right, so that's basically how you graph a polar coordinate point. Now, you'll hear this word sometime in this lesson. You hear the word pole, and when we talk about the word pole, we're talking about the origin, all right? And another thing to note that sometimes can be a little bit confusing is that sometimes you may have something like this, but if this was negative, that would actually be the opposite direction. It would actually go like that, right? And again, really, the line shouldn't be there, but that point would be basically on the other side. Does that make sense? So again, just be aware of that. That may happen a few times in here. Now, we're going to go through a crash course of polar coordinates, but hang in there, right? At first, it starts off pretty simple. Then I'm going to actually teach you how to graph some of these. So this lesson might go long somewhat, but just hang in there. Trust me, I'm doing this because I feel like I have to. Okay. So make sure you actually, and that's what I did in my homework. I kind of wrote these formulas at the beginning. All right. So I'll be able to see them. So write this on the top of your homework, and you'll notice that this are going to be pretty easy, right? So first, we're going to convert the polar points into rectangular points. And to do that, all we do is we're going to use that formula that says x is equal to r. Let me not use red here. Like x is equal to r times cosine. So this would be 4 cosine 4 cosine of 2 pi over 3. And the y coordinate, well, actually, yeah, the y coordinate would be the same thing, except for you would have a sine. So 4 sine of 2 pi over 3. All right, if you do a little bit of math, this would give you negative 2, and this is going to give you 2 square roots of 3. Okay, so this is how you found this point over here. And of course, even though I know that some of you have the unit circle memorized, I tend to write this triangle. You don't have to do it my way, but this is basically how I figure this stuff out pretty quickly. If this is pi over 6, this is 1, this would be pi over 3 over here. So this is the square root of 3 and 2. And I also normally draw this triangle for myself, where this is, that's not 1. This is 1, 1, square root of 2. And this is for the pi over 4 triangles. Okay. So on B, same idea. All right, you would just plug in square roots of 5 for R. And for one of these, you would do cosine of pi over 6. For the other one, you do square root of 5 sine of pi over 6. Okay. So for example, this would be square roots of 5 times the square root of 3 over 2. And square root of pi over 6 is 1 over 2. So this would just be square root of 5 over 2. So the answer for this one, if you multiply the first square root of 5 times the square root of 3 is the square root of 15 over 2. And this is the square root of 5 over 2. All right, so that's it for that. To convert this into rectangular points, okay, so we're going to go from rectangular to polar. What we do first is we find out that the r, we need to know the radius, right? And to figure out the radius, think about it, it's almost like a Pythagorean theorem. I'm going to grab those 2 points, and I'm going to find the length. We're going to find that length of that radius, if you will. All right, so when you do that, you get 4. And now for the angle, right? Remember the tangent, according to our formula, is tangent of theta would be equal to y over x, which in this case, that would be 2 square roots of 3 over negative 2. So this is negative square roots of 3. Okay. And let's see if we look up here, right? If we're talking about tangent, the tangent would be the tangent of, let's see, opposite. Yeah. So that'd be the tangent of, let's see. Yeah. It'd be pi over 3. Yeah. Opposite over, yeah. Okay. So this would be pi over 3. Well, actually, because that's negative, that should be negative pi over 3. So the answer to this one would be 4 comma negative pi over 3. Right on this part right here, same idea. I'm going to do this one a little bit faster. And again, the tangent of, by the way, and that is technically not proper, so I should probably say that theta over here, like I'm asking myself, where is theta? Negative square roots of 3, so yes, this is pi over 3, negative pi over 3. All right, so on this one right here, you have negative 5 over 5, so I'm looking to see where is tangent equal to negative 1. Of course, you could use a calculator than this if you really wanted to, but this would be negative pi over 4. Okay. All right, so let's go ahead and move on to polar equations. And again, this is not too bad. This is mostly just kind of a bunch of algebra and some trigonometry. Now, on this one, there's not really one certain way you need to do, but essentially what you need to remember is that by the time I'm done, y's and x's on A, B, and C need to be gone. So if somehow you're doing some work and you still have some y's and or x's in your equation, that means you need to kind of keep going. All right, so on this one, remember I have that equation at the top that says that y is equal to r sine of theta. So I can replace this y with r sine of theta, and that's equal to 4. And at this point, I'm going to solve for r. Okay, so r is equal to 4 over sine of theta. And that's it for that. Okay. Now, on B, all right, same idea. Not the only way to do it, I'm sure, but there's some way I can think of. I'm going to replace that y with r sine of theta. I'm going to replace this x with r cosine of theta. And let's see. I'm trying to get the r by itself, so I'm going to subtract. Let's see, how did I do it? I'm going to subtract the 3r cosine of theta. I'm going to leave that 2 out there. Then I'm going to factor out an r. Okay, and then finally, I'm going to divide both sides by the sine theta minus 3 cosine theta. Okay, so there's that. All right, on C, okay, y is r sine theta, x is r cosine theta. And what's going to happen after that is I'm going to go ahead and, whoop, forgot the square here. I am going to go ahead and square this. So I have 2r squared cosine squared theta. And remember, my whole goal here is to leave r by itself. So I want to get r is equal to a certain number. Okay. So again, in case you're not familiar, right? Basically, we have this function r of theta, which is what we're looking for here. So I don't think I made that quite clear, but the function, the polar function, is going to be r of theta. Okay, so now what I do from here is I'm going to subtract everything to one side. I'm going to put the r sine. I'm actually going to choose to subtract the r sine to the other side. All right, so I'm actually going to write this one here. I'm going to set that equal to 0. And then now, just sort of similar to how I did that other one, I'm going to factor out an r. Now we get that r is equal to 0 on one of these, which is not really valid, all right? So if r is equal to 0, that just means that you have a, let's see, what would that mean? That would just be a radius of 0. So what I'm saying is I'm going to set each one equal to 0 and solve. So on this one right here, this one, if I set it equal to 0, I can actually add sine to the other side. And I know some of you are thinking, well, why didn't you divide by r? Normally, I don't like to divide by r because that is a legitimate solution on there. So I don't like to just divide by r and just get rid of it in this case. But you could have. It wouldn't have affected in this problem at all. Okay, so now, again, I'm trying to get r by itself. So r is equal to sine theta over 2 cosine squared theta. All right. And you could have stopped there, but say we have multiple choice and you didn't see an answer like this, we could split that up into, excuse me, into, let's see, sine theta, no, with a 1/2 out here, over cosine theta times 1 over cosine. So this would be r is equal to 1/2 tangent secant. Okay. Now, the next few, all right, tend to be a little bit more difficult for me, but nonetheless, all right. So the first one's not too bad. If I divide both sides by, notice the secant is 1 over cosine, right? So if this is really 1 over cosine, this is the same thing as 1 over cosine, right? I can multiply both sides by cosine, and I would end up with this. And remember that my goal here is backwards. My goal is to end up with x's and y's. R's and cosines and tangents need to go away. Okay, so in this case, remember that r cosine of theta is x. So this is x is equal to -3. So that's it for that one, right? On the next one, all right, I'm going to multiply times the denominator. And again, this is obviously not the only way to do it, but this is just the way that I'm choosing to do it. Now I'm going to distribute. Now r cosine of theta is x. All right, so this is r plus 2x is equal to 4. Okay, and then now I'm going to try to get this r by itself because eventually I do want to get rid of it. So I have 4 minus 2x. Now I'm going to do something that seems kind of weird first, but remember my whole goal is to get rid of r, and I know from the top of my my formula is that r squared is equal to x squared plus y squared. So I'm going to square this side, and as long as I square both sides, then I'm good. So r squared is equal to x squared plus y squared. And this is equal to, let's see, 16 minus 4x plus 4x squared. Okay. And I'm not really sure how much more you could do. Let's see. So I'm going to subtract the x squared, subtract the y squared. I guess kind of good. That should be minus y squared. I think, did I miss a 16 somewhere here? Oh, man. Oh, yeah, I did. My bad. Let's see. That would be 8. This should be a 16. Okay, so let's see. So the rest should be the same. And I can leave it like that. Okay. So let's see what else we have here. Okay. Okay, on C, all right, example 4C, I'm going to multiply both sides to the denominator again. Let's see that I did it the same way over here. I did. Okay. So I have r cosine theta plus 2 sine theta is equal to 3. All right, and I went ahead and distributed the r. This one's not quite as terrible as the last one. And notice that on these, r cosine is x and r sine is y. So this is going to be x plus 2y is equal to 3. And that one you can solve for y if you want to, or you can leave it like that. Okay. Obviously, if you have multiple choice, you need to keep working until you get it. All right. So polar graphs. Okay. So at some point, I'm going to tell you about how to do some of this. All right. But when you have, if all your equation is r is equal to 3, okay. So all that means is that you're going to have a circle of radius 3. And if you didn't get it, you could square. I mean, r is equal to 3, right? So we can say that if I have r squared is equal to x squared plus y squared, and I replace r with 3, 3 squared is 9. So this is 9 is equal to x squared plus y squared. So hopefully now you can see how this is a circle of radius 3. Anyway, let's scroll about the graph and convert the polar equation to. Okay. All right, so now we're gonna get into some of the graphing that I was talking about. At first, I thought, well, maybe we don't have to know everything about the graphing, but the more I've kept going into this lesson and the homework, right, I kind of realized that knowing how to graph a lot of this is useful. Okay, so first, let's worry about what it's asking us to do, right? So what do you know about the graph? Okay, so this is what I know about the graph. Now, when it comes to something like this, where you just have like a number times sine or cosine of theta, right? I didn't say 2 theta or 3 theta. What that does for you is that's going to make this a circle, okay? And that circle is going to be, because it's going to be on the y-axis. So it's going to be up on the y-axis or down on the y-axis. Because I have a -3, okay, then that means I'm going to be below. So my radius of the circle is going to be 3. All right, so this right here is going to be 3. Okay, and the diameter will be 3. And the diameter, because that's 3, that means that I'm going to go about here and about here, right? Because the radius is 1.5, right? All right, so that's what that would look like. I'll do more of what it's asking me to do, but let me just show you another example. If you would happen to have, like, say, r of 4 cosine of theta, all right, then cosine is going to put your circle on the right or on the left. Okay, now, because I put 4, that would be the radius of that circle. And it would look something like this. Well, circle. Now, if it would have been a negative cosine, then it would have been a circle on the left side of diameter 4 or of radius 2. All right, so it could have been like that also. Now, if this sign that I have right here would have been positive 3 sign, then it would have been a circle of diameter. I think I keep saying radius, and I apologize for that. Of diameter 3, but it would be above. It would have been above the x-axis. So it would have been up here, essentially. Oh my gosh. Again, that. Oh my goodness. I'm having some technology problems here. It basically, again, if this would have been r is equal to 3 sine of theta, it would have been a circle of diameter 3 above the x-axis, like that. Okay, but anyway, so that's how you deal with that. I'll explain more of what I wrote down here, but I would actually say that probably need to pause the video and start writing everything that I wrote here, because that basically helps you graph almost anything that we have in this section. All right, so okay, so now that we know how to graph at least the circles, right, of polar coordinates, what it's asking us to do is we're supposed to write this polar equation as a rectangular equation. All right, so this one's kind of a weird one, and this will happen on your homework at least once, right? Basically, what they do, and I didn't really see that coming, right? Because remember, I'm trying to get rid of the 3, or excuse me, I'm trying to get rid of the r's and the signs. So I'm not trying to. I want to end up with x's and y's. All right, so this is going to be r squared is equal to -3. And remember, this is now y, and r squared is x squared, excuse me, plus y squared, which is equal to -3y in this case. Now, the answer might look confusing, and again, the only reason I want to keep going is because that's what they do, and you do have one like this in your homework, so let's do it, all right? So what happens after this is that they decide to put all the y terms on one side of the equal sign, like this. And then after that, they do complete the square. Remember, complete the square is where they grab that 3, they divide it by 2, and then they write it like this. So I have x squared plus y squared plus 3y plus 9/4. And 9/4 is 2.25. Now, whatever I just added, I have to subtract it, right? Because technically, I can't just add something to one side of the equal sign without getting rid of it at the same time. So now, when I factor this left side, this is going to be y squared plus that should be minus. Oh, no, that should be plus. Oh, no. I just realized what I did. 1.5 squared. No, that's right. That is correct. And that's going to be equal to, I'm going to add this to this side. So that's going to be equal to 2.25. All right, and that's it for that. So as you can see, this is a circle of radius of 1.5. Excuse me. Yeah. Man, I don't know how this works. Yeah, this one's a little bit weird, but yeah, the radius is a little bit weird because it's a decimal. But anyways, I do move down 1.5. Okay. And that's what happened here. So that's my radius right here. Okay. All right. So moving on. So on C. Okay. On C. So there's a lot of stuff. There's actually nothing going on. This is the whole answer. I kind of wrote it. This one's a lot easier. It's a straight line. But now we're going to be facing a bunch of other different types of, what do you call them? Type of polar graphs. Okay. Now, this is all of these that I wrote in red kind of happen to be what's going on down here. So when I talk about A divided by B, that's what I'm talking about, the first number, and then B is normally the number attached to the trig function. All right. So if A minus B is greater than 1, okay, then that's actually, I'm going to say less than 1. Okay. I don't remember if I had it like that. Let's see. No, yep, I had it the other way. All right, so if it's less than 1, then you're going to have an inner loop, okay? Now, and that's, by the way, that's pronounced limason, all right? The C has a little tail on it, so it's limason, and you're going to have an inner loop, and I'll show you how to graph this in just a second. Then you have the cardioid, that's kind of hard to say, cardioid, I don't know. If that's equal to 1, it kind of looks like the heart shape, Okay, then you have another type of limestone that where you don't have an inner loop. Okay, and that'll happen when A over B is between 1 and 2. And then finally, if A over B is less than or equal to 2, then you have almost a circle, but it's kind of flattened on one side. Okay, so that kind of leads me to what's going on over here. Okay, now what happens over here, first of all, before we go too far into this, is that the graph is incorrect. All right, now I'm going to actually teach you how to graph, and I'm going to use a different color. And again, the graph that I have here is not right. Okay, so I'm going to show you what I mean first. So the thing that I didn't say, okay, is that kind of like the circle, if this is negative right here, okay, and it's a sine function, so the graph is going to open downwards. It's going to be on the bottom, all right, not on the left like they have it. They actually graph the cosine. So what you do here, it's first A, all right, which is this number right here. It's 1. First, you're going to draw, this is like your A value. So I'm going to call this like negative A and positive A. That's really how you start. And then you have basically on the inner loop part, and that's kind of the part that's a little funny, but all of these that I'm about to write kind of apply to almost all of them, all right, except for you basically do have to know this, right? Like you have to know it in order for you to know what I'm talking about here. So first, I'm going to have A minus B, or the absolute value of A minus B, which in this case is going to be the absolute value of 1 minus 2, which is going to be 1, okay? Now, you got to know that that right there is going to be down here, okay? So again, this part right here, well, I'll write it later so I don't confuse you completely. And then you have A plus B, and then A plus B, which in my case would be, and by the way, and when I say A and B, they should be positive, okay? Don't put a negative with the B. So A plus B would be 2 plus 1, which is 3. So again, whether it's for this equation or the last one, right, those numbers need to stay basically A is a positive value and B is a positive value, and you just got to keep those signs, all right? So in my case, A was 1 and B was 2. So let's make sure we get that clear. So that right there is going to be over here. And that's about as much as you're going to get. All right. So what you do here is you start from the pole, from the origin. All right. And we're going to go up above. I'm actually going to follow this for some reason. And then it doesn't have to be perfect, right? It's just a sketch. And then we're going to go down. We're going to go through this one. And again, it's probably way more circular than this, but. And then you go above and you go through it, and then you go through the loop like that. Okay. And again, this point right here was A minus B. And that point right there was A plus B. Okay. And again, there's a lot of stuff that I looked at about graphing. I'll attach a video on Google Classroom and maybe even on the YouTube video also, so you can just click on those links. There's really tons and tons of videos of it. I found one that just kind of included a lot of this, and I think that was a lot of help just to kind of get started on this. Okay, so that kind of renders like, so what they're saying here, okay, is that they plug this in and pretend like this is my polar function. All right, so when they plug that in, they got the values and they're just asking like, what do you know? Why are these negative? Now, that's the weird part, right? If we were to graph this just point by point, like for example, pi over 3, which would be the easiest one to graph, would be over here. Pi over 3 is here, by the way. Okay, and notice that it's a negative, right? So the radius would be negative, which that's why you have this point on the inner loop. Okay, and I don't know if you can see, maybe I should use a different color here. This is why you would have maybe this point right here and the inner loop, okay? So what happens is that all these negative values is what happens when basically when you're creating the inner loop. So all those negative values correspond to the inner loops. Those are like the coordinates of the inner loops and the limison. All right, so when it's asking us for this, I guess we can say that R values are negative when the inner loop is created. So as far as we know, it's being created between pi over 6 and 3 and 5 pi over 6. So remember, don't be too confused, right? The R values is basically like it would be the length of that radius. So basically, if we're talking about our polar function, this would be theta and this would be R. Essentially, again, that would be theta and this would be R. Okay. All right, so let's go ahead and move on from that. Now we're going to talk about finding the derivative of a polar and polar form, finding the tangent line. So kind of like the parametric, very similar, right? If you want to find dy dx, you have to find the derivative of y with respect to theta over the derivative of x with respect to theta, which is what this is saying. All right, and for the horizontal tangents, obviously, if this is equal to 0, that means that this is 0, and that's y, provided that the bottom is not equal to 0, right? So essentially what we're looking for after a while is that we're going to look for, and I said that wrong. My gosh. I wish they would do the notes like I wanted to. Anyway, so the horizontal tangents is where the y is 0. So again, notice it's just the top part. If the top part is 0, then that's where you have the horizontal tangents. On the vertical tangents, obviously, as if the bottom of this is 0. Okay, now you don't have a conclusion. You don't know what you have if both dy over d theta and dx over d theta are both 0. So let's go ahead and just head to a problem and let's see what we can do here. Okay, so notice again, if we were talking about the graphing part, okay, so I know that a lot of you might have been confused when I did this. Remember, this one, A and B are the same. Right, so A is 1, B is 1. So that would fall under the, let's see, this one that kind of looks like a little bit like a heart. Okay. Now notice that I still have cosine means it's going to open to the right. Okay, this is the A value, 1 and 1. Okay. And then right here you have like A minus B absolute value, which in this case is 0. So that's where you start here. And then let's see if we add 1 plus 1 here, which was what I call A plus B later on, that was 2. All right, so that's, you can see that what I told you actually works on this also. Okay, so now that's not, they're not really asking us to do this, but I just wanted to show you. All right, so we want to find all the points and the, I don't know how to say that, cardioid that has a vertical or horizontal tangent lines. All right, so first we want to get this in terms of x. All right, so remember that x, flip the page here. I don't want to make any mistakes. All I'm doing is I'm still using that function that says, or that formula that says that x is equal to r cosine theta. All right, so, but instead I will replace the r. I'm going to replace the r with 1 plus cosine of theta. All right, so again, I replace this That was r. Okay. Originally. All right. So now if I distribute, okay, I'm going to go ahead and take the derivative with respect to theta. So this would be negative sine theta minus 2 sine theta, and I had to use the chain rule on that one. Oh, I did that backwards. I meant to say 2 cosine. 2 cosine theta sine theta. I guess it really didn't matter how I wrote it, but if I was using the chain rule, that's how I would write it. Okay, and then I'm going to go ahead and do the same thing for the y coordinate. All right, so I'm going to write the y over here because I think I'm going to run out of room. So y would be 1 plus cosine theta times sine theta. All right, and y is equal to sine theta plus cosine theta sine theta. And now I'm going to take the derivative of that with respect to theta. So this would be, let's see, cosine. And on this one, I have to use the product rule for this. And when I do that, I ended up with cosine theta squared, cosine squared theta minus sine squared theta. Okay. So now it wants to know, as vertical, find the points. All right. We're trying to find the points where I have a vertical and a horizontal tangent lines. All right. So for the horizontal, for the horizontal, let's see, dy y prime. Okay. So I need to know when y prime is equal to 0. All right. And y prime is equal to cosine theta plus cosine squared theta minus sine squared theta. And again, I'm setting that equal to 0. Now, I'm sure you could use a calculator, but let's say that you weren't. Since all of these are already cosines, I'm going to use a trig identity to convert this into 1 minus cosine squared. And then that will leave me with 2 cosine, 2 cosine squared theta plus cosine theta minus 1. Okay. So when you get to this part, okay, now, again, if you're doing this by hand, and we are, okay, is how would you solve for something like this? Now, notice that I do, even though I have trig in it, I do have a square function. So if I pretend that this cosine is x, then I would have 2x squared plus x minus 1. So I could either try to factor, but this is unfactorable, or I could do the quadratic formula, which is what I'm about to do. Okay, so again, x, which was cosine, if I use the quadratic formula, x would be cosine, so that would be b, which is the coefficient of cosine, which is 1, or negative b, excuse me, plus or minus the square root of b squared, which is 1 squared, minus 4a. A is the coefficient of cosine squared. AC, C is negative 1, all over 2a. Now, 2a would be 2 times 2, right? Okay. So if I do all of that, I would get negative 1 plus or minus 3 over 4. So cosine theta, I don't know what happened to my theta. Cosine theta would be equal to 1/2 and negative 1. Well, it doesn't matter, but I'm going to write them backwards here. Negative 1 and 1/2. in ascending order, I guess. So then I have to think, where is the cosine? Where is cosine -1, which hopefully you know that's pi, and where is the cosine equal to pi over 2? Excuse me, pi over 2, 1/2, which is going to be located at pi over 3, plus or minus, really. All right, and I know negative pi over 3 would be the same thing as 4 pi over 3. Yeah, but we're just going to leave it like that. Okay, so same thing. If you wrote that, that's fine. It doesn't matter. Now, we're going to do the same thing. We're going to do the same thing to find out my vertical tangent. So again, so this is for the horizontal part, and this is for the vertical part. Okay. So I'm going to set my derivative with respect to theta, so of x. So on this one, I'm going to set this equal to 0. And this one's a little bit easier. I could factor out a sign, or in this case, I'm going to choose to factor out a negative sign. And that's going to leave me with 1 plus 2 cosine theta is equal to 0. So I have sine of theta is equal to 0. Whoops, that looks crazy. What happened there? Or negative sine theta is equal to 0. And then 1 plus 2 cosine theta is equal to 0. So this is the same thing as having the sine of theta is equal to 0. And this is the cosine of theta is equal to negative 1/2. Okay, so notice that on this one, where is the sine of 0? Well, that's normally on 0 and pi. And where is the cosine negative 1/2? Well, that's going to be located at 2 pi over 3. And at 4 pi over 3. Okay. So, okay, so the only thing you have to watch out for is that I can't add half 0 over 0. So if you see a theta that's the same number, I can't use that because it's going to be inconclusive. You understand? So again, for example, notice that right here I have a pi and a pi, so I can't use that. And let's see, there's surely something else I can't use on here. See, 4 pi over 3. That would be the same thing as... Oh, let me not get all fancy here. And I think I only did that because of the note. So you got pi over 3 for sure. Let's see, cosine. No, the cosine is positive on the other side. Oh, okay, no, we're good. We're good. I said that wrong originally. Negative pi over 3 would be this angle over here, which technically that would be what, 5 pi over 3? Yeah. So 5 pi over 3 or negative pi over 3 is the same thing. So we're good on that. I was trying to make sure that the 4 pi over 3 was not the same thing as negative pi over 3, which is definitely not. So we're good. So I'm sorry. I said that wrong the first time. Anyway, so therefore, my horizontal tangents will be officially on positive and negative pi over 3 for sure. And my vertical would be located at 0, 2 pi over 3, 0, 2 pi over 3, and 4 pi over 3. Okay, moving on. All right, so now, as far as the next part, all right, example number 8. Now, this is a different type of graphing, right? First of all, before we get too far, all right, it says the tangent line at the pole. Remember, the pole is basically the origin, and that will happen first if, let's say you have this angle theta, and you plug it into your polar function, and you get 0, and the derivative at the same place is not 0, then it is considered a tangent at that pole. Okay, and again, that sounds really complicated, but you'll see it's really not that bad. So now, I'm pretty sure the only reason I even looked through this is because on the homework, it's asking you to graph, like to know what the graph looks like. And I guess they assume you have already done some polar coordinates and pre-calc, but pretty sure you didn't. So, anyways, so this is actually going to look like a pedal, all right, or pedals in this case. And I wrote a couple of things that, again, I think will help you. For example, this is the original function. So if a function looks like this, okay, where n is something greater than 1, I suppose. I guess it could be 1, so it will just look like a circle. But if you have something like that, like sine or cosine, all right, now the opening left and right, that's not really going to matter in this one, so don't focus on that. If you have an even number, so for example, the sine of 2 theta, okay, then you're going to have twice as many pedals. So if you have sine of 2 theta, that would be in polar coordinates. I mean, in polar, as a polar function, that would be a flower-looking polar equation that has 4 petals. All right. Now, if you have an odd number inside of here, like I do now, all right, then this one will have 3 petals. Okay. And then I wrote some stuff that might help, but this only helps with the odds. I don't really know how much that helps. So let's talk about that here in a second, and I'll show you how it is that they graph this one in just a second. All right. So first, let's answer the question they have for us. Right. We want to find dy dx. Right. So first, I want to know what x is, and then I want to take the derivative of this. So I have x is equal again. I am using the same formula from the beginning of these notes, where this is r. So remember, x is equal to r cosine of theta. So I just replace r with this, okay? And then y would be the same thing, except for you would have 4 sine of 3 theta times sine. Okay. So now, I'm going to take the derivative of each one. I'm going to put the derivative of y with respect to theta on top, and then derivative of x with respect to theta on the bottom. Now, I already wrote this. Now, I am really hoping that I did this right. I think I did. I checked the notes, but sometimes the notes and I could be wrong. But I think we're good. I don't know if you can hear it, but my dogs are just barking up a storm. Okay, so let's start to the derivatives. Check it out. I had to use a product rule on each one. All right, so that's the derivative. Now, before we go on to calculating the slopes of the 3 tangent lines at the pole, okay, let me talk about how they were able to graph this. Okay, so first, what they do is, let me erase this so you can't quite see it yet. And I'll show you how it is that I got this here. So essentially what I know is that this length is like and you can actually tell, let me switch that to red here, that the length here is 4. So 1, 2, 3, 4, right? So I know that is only going to happen, right? The r, the length of that radius is going to be 4 right there. And then I set that equation equal to it. And then essentially I solve for theta, right? Divide by 4, figure out where sine of 3 theta would be equal to 1, which in this case is pi over 6. So that gives me the first, if you will, the first location of the first pedal, right? To figure out where the other 2 pedals are going to go is that you have 2 pi, and that because I know I have 3 pedals, I can divide that by 3. So I know that my pedals are going to be located every 2/3 pi, and n just stands for, like, it's a whole number. Just every 2/3 you're going to have a pedal. Now if I do 2/3, right, 2/3 will be, let's see, that's 1/3, that's 2/3, so that would be the other one right here, and this is 1/2/3, so this is the other one. And if I keep going in a circle, you'll notice that I'll end up in the same place. Okay. And again, if you don't believe me, multiply 2/3 times 3, and you should get 2 pi, and you do. All right. So once you have those 3 points, then you can actually draw your pedal from the pole, from the origin. Okay. There's definitely more to this than this. There's plenty of videos out there that tell you like every single little thing about these, and I encourage you to go watch them if you're interested. But for now, that's all we need. All right. So, now we're gonna try to figure out the polars. We're gonna try to figure out, since it wants to know the slopes at the pole. Remember, the pole is at the origin. Okay, so I'm gonna do this other thing over here. So this is not related to graphing here, but what happens is that to find the polar zeros, I'm going to do something similar to what I did there, but okay. To find the polar zeros, in this case, I'm going to set this equation equal to 0. So it's going to give me sine of 3 theta is equal to 0. And where is the sine of 0? Where is sine 0? We know that, oops, I almost put a pi there. We know that the sine is 0 at 0 and pi, for example. So every 0 and pi and above that, it just keeps going, right? So I'm going to write this as n stands for example, if you plug in a 0, you get 0. If you plug in a 1, you get pi. If you plug in a 2, you get 2 pi. Okay, so essentially what I have here is that, but now I'm going to divide that by 3. So that's going to give me that is going to happen at every pi over 3 values. Okay, so that allows me then to figure out the slopes of those tangents, which is what I'm going to try to do. I'm going to just plug in a 0 for my derivative, and let's go ahead and pretend like we did, because this video is already gone pretty long. I'm going to plug another one at pi over 3, but I think the trick here was just to figure out where, even though this is how they got it, by the way. Right? On your homework, I'm pretty sure that I tell you where the poles are at. So that's the entire reason why I put this. All right. So then the next one, let's see, if I plug in a 2 here, that would give me 2 pi over 3. So theta is equal to 2 pi over 3. So when I do that, I get negative square roots of 3. Okay. Okay. So let's see. Apparently we have a, let me use a different color here. And I didn't really need, and this is pi over, let me do the 0 first. There's the first one. Let's see, what's the other one? Pi over 3. Pi over 3 is here, and it goes all the way through. And then you have 2 pi over 3. 2 pi over 3 is right here. So those are the lines, all right? But the slopes on these then therefore would be positive, negative, square roots of 3, and then of course you have 0. So y prime is 0 here. So again, you have those lines, and then you're just looking for the slopes, right? So that's how you found it. Let's see. Now, on C, first of all, it's asking us to find the horizontal tangent lines, right? So all we have to do is, which, I don't know, have we done that already? Oh, not for this one. Okay. So for this right here, what we have to do is set the derivative equal to 0, but to be precise, right, since we don't want to waste a whole lot of time here, really all I have to know is when the numerator is equal to 0, meaning all I have to do is find out when dy d theta is equal to 0. Now, I'm going to write what dy d theta was, and I remember we did that earlier at the, like, on part A of this. We're going to set that equal to 0. And you could, and that's what they're doing on here. They put this in their graph, not in polar coordinates, just in their regular f of x function. And they figure out the x values here. So this is 659. This was 0. This right here is pi over 2. And you can kind of tell what that would be pi over 2, and pi also is one of them. But these, you probably need your calculator for that. So you got 2. I put a negative there for some reason. 2.182. 482, excuse me. All right. So those are the points, right? So I'm going to write theta is equal to 0, 0.659 pi over 2. I mean, the pi over 2 you can hopefully tell, right? Because they both have sign in it. So 2.482 and pi. Okay. So what happens after that? Okay, so discussing its significance. Really, what we found, if you were to plug in each one of these back into the original function, which is this one, all right? There is one of them, which is this one, right? Pi over 2. That will give you the minimum, that would give you like the maximum r value, if you will. And the r value is just the radius. So it would give you that. And the other ones, and by the way, the reason it's pi over 2, remember, we're looking for horizontal tangents, right? I'm not really, and let me change that color not to confuse you here. So basically, that's a horizontal. This is somewhere a horizontal, so this is probably one of the ones we found. This is another one. And we also have 0 and pi, which is along the origin. So, but that's probably, and I'm guessing those 0 and pi would probably give you 0 in the denominator also. So that's probably why we don't use those. But anyways, the significance is that you just basically one of them gives you the minimum here, and to just find the horizontal asymptotes. The horizontal tangents. Not really sure what else they want me to say on that. All right, now on D. And again, we're almost done. Thank goodness. Okay. So to find, remember that means the length of R. Okay, to figure that out, it's actually not too hard, not too bad at all. First is I'm going to say that to figure out this right here, you have to set, well, I guess technically you would set, what was this original function? 3 sine, 4 sine, okay. You know the maximum, right? The most maximum this could be would be 4, kind of similar to how I graphed it earlier. Except for this have to be plus or minus 4, because it could be negative. Remember, this is like the absolute value, right? So I have plus or minus 1 is equal to the sine of, and I wrote theta instead of 3 theta. My bad. Okay. So now, and it says there are 3 points. Okay, so that's going to happen at, where is the sine -1 and positive 1? Well, it's positive 1 at pi over 2. It's at 3 pi over 2. It's negative. Now, we're going to go one more, only because by the time I divide this by 3, you'll see that I'm going to stay below pi. And I guess, and technically, since I graphed them, I mean, we already found these, but so you can just think back of when I graphed them. I think that way, honestly, for me at least, it's a little bit, makes more common sense to me. Okay. Now, anytime I added pi over 6 plus 2/3, that's what I ended up getting, right? I ended up getting pi over 2. Actually, this, which is the same thing anyway, I ended up getting a negative 3 pi over 2. Excuse me, 3 pi over 2, which is here. But same idea, right? So anyway, after that, what I'm going to do here, it would give you the same thing, do not worry. So I'm going to figure out, it says shows that the tangent line is perpendicular to the line segment to the point. Okay, so for this one right here, I'm going to figure out what is the derivative of pi over 6, which was the square root of negative 3. And remember that the slope, all right, that is perpendicular is a negative reciprocal, which would be, well, let me write all of these first, then I'll go on. Pi over 2 5 pi over 6. Whoops. Something's going wrong. Okay. Now, let's see. Show that the tangent line is perpendicular to a line segment to the connecting point. Okay. So this would be square root of 3 over 3. Technically, it would be 1 over the square root of 3, but so again, perpendicular ones. This would be undefined. And this one, this is the easier one to tell. Because pi over 2, the reason they call it pi over 2 is because they're talking about this entire line. All right. Now, that line right there, right? Let's see. Yeah. The derivative here is 0, and that would be the opposite here. This is the opposite slope, so you can tell that that's perpendicular there. Now, as far as the other one, that would probably take more work for sure. see, 5 pi over 6. What the hell? Oh, man. Oh, yeah. Okay, never mind. 5 pi over 6, yeah. We're good. Negative reciprocal, so this has to be negative here. So what's going on this one, right, is that these right here are those slopes that I just found. Okay. All right, so we're back to something semi-familiar with, which is right at the equation of a tangent line that passes through that point. Now, because it is talking about a line, we're going to have to convert this into rectangular form. So first, we need to figure out the point. Okay, so the first thing we have to do is convert this back into rectangular form. So remember, r is 4 and theta is pi over 6, right? So this would be, the x value would be 4 cosine of pi over 6. And my y value would be 4 sine of pi over 6. This right here would be 2 square roots of 3, and this would be 2. So there's my point. I have it. Now, step number 2 is I need my slope, okay, of the tangent line pi over 6. Now, I don't think this is the only way to do it, but because we already done it once, the tangent line, all right, I have to plug this in into my derivative function. That'd probably be the easiest way to do it, to be honest. And since I've already done that before, that's negative pi over 3. Excuse me, that's negative square roots of 3. And then finally, so I just have to write the equation of a tangent line. So I have y minus 2 is equal to, my slope is negative square roots of 3, x minus 2 square roots of 3. Let me check here. Yep. Okay. Well, that's it for that. And again, what we just found is the equation of this tangent line, which more or less is what we could have done here. We found all the slopes that were perpendicular to that point. But anyway, I know that was really long, guys. I apologize. There was a lot of stuff packed into this one lesson, but that's just what we have to do.